Managed AI agents present a unique structural problem. They can execute complex logical reasoning, but their runtime environment is completely isolated from the real-world data required to do useful work. On the left, the managed container loaded with built-in tools. On the right, your local infrastructure. When the agent uses built-in tools, the harness handles the request server-side. The loop executes invisibly, requiring zero participation from your application. That model functions perfectly until the agent needs proprietary data. Internal records and live inventory sit on your network, behind strict auth walls. The managed container has no way to reach them. A common mistake developers make at this juncture is trying to force the agent's server-side container to pierce their secure network perimeter. Bridging this gap requires abandoning the server-side execution model. You have to invert the architecture. Claude custom tools function as a bridge, moving the execution from the server-side harness to your local application. We call this execution inversion. The agent no longer executes the task. Instead, it emits a structured request, and your local application performs the work. Because the execution logic and auth credentials stay within your network, the agent can interact with internal systems without the managed container ever gaining direct access to your infrastructure. Before an agent can request your local data, you have to define exactly what operations are available to it. It needs a strict contract. Take a look at this declaration. A custom tool requires 3 specific components: a name, a JSON input schema detailing the exact arguments, and a natural language description. That text description is not optional documentation. It acts as an API specification and a behavioral instruction manual for the agent. The agent relies on those sentences to decide when and how to fire the tool. For instance, if you add the rule, always look up a vendor ID, never guess, you are establishing a behavioral constraint directly guiding the agent's logic to plain text. The top half shows server-side execution. When the agent calls bash, the stream flows continuously. Now observe the bottom half. When we trigger a custom tool, the execution stream halts, changing your role to an active participant. This halted state is not a timeout. It is a deliberate architectural pause. The agent is currently waiting for you. The entire session freezes in its place. It cannot move forward until your local code resolves this pause. Managing the structural pause is the technical requirement for wiring the connection between the managed sandbox and internal APIs. Managing that pause requires a 4-step handshake between the agent and your local code. Step 1. The agent emits an event carrying the specific parameters. It states, "I want to execute this operation." Step 2. The session goes idle, logging the specific event IDs that now block the stream. The agent is blocked, waiting on your infrastructure. Step 3. Your application executes the query against your database. To hand data back, your code pushes its answer to the stream using an identical matching event ID. Step 4 is the resolution phase. The harness verifies the IDs match. Once satisfied, the session flips its status back to running. The agent resumes its thought process, analyzing the internal data you just retrieved. The execution harness does not care how you retrieve the data. It only verifies that every blocked ID received a matching answer. This ID mapping logic is what allows asynchronous local operations to safely feed data back into a synchronous managed agent. Because this handshake requires precision, there are 2 specific failure modes that will cause your event loop to fail silently. The first failure mode is a mismatched ID. If your local code returns an invented or incorrect ID in the payload, the harness rejects it. To the developer, the agent appears to have frozen entirely. It hasn't frozen. It received an answer to a question it never asked, and it continues waiting for the original request to be fulfilled. The second failure mode is partial resolution. Agents fire multiple tool calls at once. If your loop only processes the first call, the remaining requests are left unanswered. The session only unblocks when every single event ID in the array has a registered result. A robust implementation avoids this by iterating through the full array of event IDs on every loop to ensure no request goes unanswered. If the agent can request internal data, how do we govern permissions and access control? Custom tools bypass the standard approval machinery and IAM policies that restrict built-in tools. Returning to our diagram, execution happens entirely within your local code, meaning you hold the decision authority. Your permission model is standard conditional gating. If a request is out of bounds, your code returns a string, saying so instead of querying the database. You get granular access control natively without needing to maintain separate policy files. This local execution model also resolves the edge case of massive data returns. What happens if your database query returns a payload so large it threatens to overwhelm the agent's context window? The harness automatically intercepts any output exceeding 100,000 tokens. It writes the full dataset to a file inside the sandbox and hands the agent a truncated preview. The agent can then use its read tool to access exactly what it needs without crashing the session. Built-in operations require an external leech because the server-side harness executes them. The agent asks, the code answers, and the managed session integrates the internal data it needs to finalize the operation.